All right, now moving on to the fourth reaction. So we're going to take a look at right now. So let's take a look at what is called a single displacement reaction. Now, if you look at the definition, it says a chemical reaction in which one element replaces another element in a compound. So I'm going to kind of talk about this the way that we talked about it in class. If you remember, we had the kind of scenario set up where we said that we can kind of think of this as being a dance. And basically what we have is we have a individual person dancing by themselves, which I'm just going to end up calling metal one. So this person is sitting there, they're kind of just dancing, hey, dancing, enjoying myself, dancing by myself. And then if we look at M2B, that is a metal in this case, which is our M2. And we've got our non-metal. Oops, non-metal. And they're dancing together as well, which means that, hey, they're an ionic compound. Now, this metal one is basically saying, hey, you know what? I want to cut in on this dance here. I'm tired of dancing by myself. I would like to actually dance with a non-metal. So what metal one is going to do is it's going to tap metal two on the shoulder and say, hey, excuse me, I would like to go off to the dance with a non-metal. Now, whether metal one can bump off metal two is really dependent upon how strong metal one happens to be. If metal one is strong enough, then what it will do is it will bump off metal two, and metal two will now be down here dancing by itself. And now metal one is now going off to the party with the non-metal. And now we have this new compound that's being produced. This is what's playing out when we look at a single displacement reaction. We're always going to have one, in this case, metal dancing by itself. Another metal is going to be attached to a non-metal. And once again, we're just going to look at the metal trying to bump off the other metal. So if we look at some examples here. Oh, and before I talk about the examples, let me point one thing out. Ionic compounds in these single displacement reactions are going to be in the aqueous state. If you remember, in the combination and also in the decomposition reactions, we said they were going to be crystalline solids. In order for this reaction to actually take place, these ionic compounds have to be dissolved in water. So you're going to notice that when you start seeing these ionic compounds, they're going to be in the aqueous state. So if we look at it, this is an example of where I have this potassium, and it's simply, once again, tapping on the shoulder of the sodium. In this case, it's going to bump the sodium on, and now potassium is going off to the dance with the chloride. And keep in mind that because these are ionic compounds, they are being put together based upon their charges. So ionic compounds are always put together based upon their charge. So this next example here, we'll take a look at a little bit later on in the notes. So we'll come back to that one. So we're going to look at is we're going to look at metals displacing metals. And that's what it says right here, metals replacing metals. And if you remember, hydrogen is a non-metal, but hydrogen is also confused because hydrogen wants to react like a metal. So hydrogen has a tendency of taking on a positive charge. And if you remember, all the other nonmetals, they want to form these anions. But hydrogen, it wants to kind of exist like a metal in this case. So what I'm going to tell you is in this case, the potassium is strong enough to bump off the aluminum. And later on in the notes, I'll explain how you'll be able to figure out whether potassium is strong enough to actually bump the aluminum off. But I'm going to tell you now it will. So what's going to happen is the aluminum will get bumped off and it will simply now be by itself. Potassium, which has a charge of +1, nitride, which is a charge of 3-, these two will go to the dance, and if we look at it, they gotta be electrically neutral to form that ionic compound. And then if we look at the states, we simply said that, hey, metals we know are solids. Only metal that's not a solid is mercury, which is a liquid. We said ionic compounds are gonna be aqueous. You're a metal, you're a solid, and you're gonna be aqueous. And now the only thing you need to do is just balance this. I see 3 potassium, so let's put a 3 here, and it looks like it's now all balanced. If we look at the next example, we've got zinc, who's going to bump off the hydrogen in this case. So what's going to happen is hydrogen is going to get bumped off, but got to be careful with hydrogen. Hydrogen is a diatomic, so we got to put that subscript 2 here. Zinc has a charge of 2+, Chloride has a charge of -1, so when the zinc and chloride go to dance together, we need two of those chlorides to cancel the charge out. And once again, states, you're a metal, you're a solid, you're going to be aqueous, you're going to be a gas, and you're going to be aqueous. And don't forget to balance these out. So let's balance it. And what we got here is it looks like we need a 2 to go here, and now it's balanced. All right, the next one, let's take a look at this one. This one is a special case that I kind of talked to the class about. One of the things that I told you, this is kind of like one of the most commonly missed single displacement reactions. And for this particular reaction, the reason why it's drawn or written incorrectly is the way in which students actually approach it. Somebody choose a different color pen. I'm going to erase this once I'm finished, but I'm going to show you what a lot of students will do when it comes to this problem, which is incorrect. They'll say, okay, well, sodium, you're going to bump off hydrogen. So hydrogen is going to be produced. But then they simply say, okay, well, sodium is going to end up going off with the oxide. So sodium is a +1, oxide is an O2 minus, and they'll write down the other product as being Na2O. And this is the problem here. It seems logical if water was made of H+, two H pluses and OH minus, that it would produce the sodium oxide. But when we think of water, water is not made up. It's not made up of a H plus and another H plus and a O2 minus. The way that water is really made up of being H plus. So let's do this here. Let's look at the real way. So I'm going to change this back to red. Water is made up of H plus and also OH minus, which means that when the H plus comes together with the OH minus, it produces HOH. Now that's technically the way in which water looks. But for convention, they simply said, hey, you know what, let's write it this way. There's two hydrogens inside that formula and one oxygen, so we're going to say it's H2O. But you have to remember that it's made up of H plus and OH minus. So let me explain how I would approach this problem if I was given this one. I would go in here and I would first say, okay, this is water in a single displacement reaction. I'm going to write water as being H plus OH minus. When hydrogen goes in here and bumps off the hydrogen, we will get the diatomic hydrogen being produced. But now if you look at it, we're going to get the sodium cation, and also we're going to get hydroxide, which means that the compound that's being produced is going to be sodium hydroxide. And then once again, it's right back to saying you're a metal, you're a solid, you're just water. So water is just going to be a liquid. So that's all it's going to be. Hydrogen, you are going to be a gas. And then the sodium hydroxide, you are going to be aqueous. And then just balance this out. It looks like we need a 2 here, a 2 here, and a 2 right here. And now it's balanced. So don't forget, when it comes to water, you gotta be careful with it. It's gonna be, once again, H plus and OH minus. If you look at that way, you'll always get that metal going off with the hydroxide as your product. All right, here we go. So one of the things we have to look at is we gotta kind of look at how we can find out or figure out whether a metal is actually strong enough to bump off the actual other metal. Because one of the things that we're going to see eventually is that if I gave you a reaction like this one here, copper plus potassium chloride, and if we looked at this reaction, copper will bump on the shoulder of potassium chloride and say, excuse me, I want to cut in on this dance. But the problem copper has is copper is not strong enough to force the potassium away from the chloride. And if it's not strong enough to push it away or displace it, then nothing is going to change, which means that we are looking at no reaction. Now, the question that you probably have is, how do I know which one is going to be strong enough to displace the other one? And the way that we're going to figure this out is we will use what is called the activity series of metals. And the activity series of metals is nothing more than just a table that ranks the metals according to their strengths. And what you'll notice is at the top of the table, you'll see lithium. Lithium is going to be the strongest metal in the list. So we'll consider that to be, I don't know, maybe the, I'm trying to think of a person who's really strong, the Rock Johnson. So we'll say the Rock Johnson will be lithium. And then down here, we've got gold, and gold is going to be that weak element. So just a little weakling here, which means that if we look at it, lithium is capable of displacing everything underneath of it. If we look at potassium, potassium can displace any metal underneath of it. However, it cannot displace anything above it, so it would not be able to bump off lithium in this case. So all you're doing is literally just looking at the actual list and just checking to see if the element falls below it that it's trying to bump off. If it does, bump it off. If it doesn't, then you're going to have to simply say no reaction, and we'll see some of that in a second. A couple of things just to point out. One, you'll notice that for hydrogen, there's this special note. It's all capitalized with a little asterisk there. It says, note concerning hydrogen. And basically what they're doing here is it's two pieces of notes that's being supplied to you. One of the notes is simply saying that, hey, lithium through lead. So let's look at it. Lithium all the way down here to lead. So all of these elements, our metals, are capable of bumping off a hydrogen inside of an acid. And remember, the basic backbone of an acid is some hydrogen attached to the X, which is our anion, and it's in the aqueous state. So these metals can bump the hydrogen off if we had an acid in a single displacement reaction. The next note where it says lithium through sodium, so going lithium through sodium, it says that lithium through sodium is capable of bumping off the hydrogen inside of water. And basically what's going on here is that the acid and the anion are not really holding on to each other that's as strong. So there's a lot of different metals that are capable of bumping that hydrogen off. But when you look at the water and we look at this H plus, remember, think of water as H plus and OH minus, these two are really holding on to each other. And because they're holding on to each other with a lot of force in this case, it just takes some really strong metals to be able to pull that hydrogen away. So not all metals are capable or strong enough to be able to achieve this. All right, a couple of things to point out once again. The metals that are actually towards the top, we consider those to be more reactive. The ones that happen to be at the bottom are actually going to be considered to be less reactive. And if you look at the bottom down here, you'll notice you have things such as silver, platinum, and gold. And if you think about our gold necklace or our platinum rings, we don't want those things to be reactive. We want them to actually be the weaklings. Because if they are the weaklings, you're right, the weaklings, then that means that they are not going to displace anybody, which means they're always going to simply be dancing by themselves. And when it comes to things such as the gold, silver, and platinum, that's what we want. We don't want our gold to start dancing with some other element and producing some rust or some other compound. We want it to stay as that pure element. And that's why when you look at these sort of metals down here, these were some of the first actual elements that were discovered because you can pull them out the ground because they're pretty non-reactive. It's hard to find something such as lithium in the ground because if you had a piece of metal of lithium in the ground, it's going to readily react with something and produce some compound. And when it's a compound, it's no longer the lithium metal in this case. All right, just pointing that out to you. So let's look at it. Basically what's going to happen is you will be given the activity series. So I will provide you the activity series when you take your test. And it will look just like this activity series right here. So I'll have the special notes on there as well. And basically what we'll do here is we'll use this activity series now to kind of figure out whether or not our single displacement reaction will take place. So for instance, with this first one, I don't know whether or not iron is strong enough in this case to bump off the copper. But what I can do is I can go up here to my activity series of metals and I'm just going to take a look at it. I'm going to find iron where iron happens to be. Let's see, iron, where are you? Right here. And then I'll find copper, which is down here, and I can clearly see that, yes, iron's above copper, so iron can displace the copper. So what's going to happen is the copper will go off by itself. So here we go, Cu. Then the iron is now going off to the dance with the sulfate. So iron is Fe, sulfate is SO4, 2 minus. Now, iron is a type 2 cation. So type 2 cations, we go to the periodic table, we're not going to know what their charge is going to be. And remember, we said type 2 cations, they have more than one charge. Keep in mind, if you ever have this problem with a single displacement reaction, just realize that this type 2 cation is going to have the same charge as that type 2 cation that happens to be in the metal, or excuse me, in the ionic compound. So if I look at copper here, copper is a 2 plus charge, which means that the iron is going to be a 2 plus as well. So just take whatever charge of that metal that's sitting there with the ionic compound and transfer it to that type 2, which means that the products will now be Fe, SO4. Charges cancel out. Don't forget, we said single displacement reactions, ionic compounds are aqueous. Hey, you're an ionic compound, you're an ionic compound. Aqueous, aqueous. You're a metal, you're a solid, you're a metal, you're a solid. And then it looks like it is already balanced, and I'm done here. If I look at the next reaction, I've got lead, and lead wants to go in here and it wants to bump off potassium. So let's see what's going to happen here. I'm going to go up and take a look at lead and see if lead is above potassium, and let's see. Lead is going to be right here, down towards, where did I lose the lead? Here you go, lead is here, and potassium is up here. So lead is trying to bump off potassium, but unfortunately, lead is underneath of it, so it's not strong enough to bump the potassium off. So I'm going to write down right here, no RXN. So if I was to take this solid piece of lead and put it in potassium chloride, absolutely nothing is going to take place. So no reaction is going to take place here. The next one we got aluminum. And aluminum wants to bump off the hydrogen inside of that acid. And let's see, we said if it was a acid, we said that lithium all the way through lead was capable of bumping off the hydrogen in the acid. So in this case, let's see, we're looking at aluminum. And if you look at aluminum, hey, aluminum falls right here. So yes, it is capable of bumping off the hydrogen in the acid. So here we go. We're going to simply have hydrogen going off to the diatomic. And then you're going to end up having now aluminum, which is Al3 plus, and then chloride, which is Cl minus. You get AlCl3, ionic compound, aqueous. You're a gas, you're aqueous because you're a compound, and you're going to be a metal, so you're a solid. Balancing it out, it looks as though we are going to have to go with a 6, a 3, a 2,